In the previous video, we had discussed about the important features of the quantum mechanical model of the atom. In this video, we are going to be talking about quantum numbers. So, first of all, the basic difference between the Bohr's model and the quantum mechanical model was the fact that we refer to the location or the space around the nucleus with the maximum probability of finding the electron as orbitals. Whereas, according to Bohr, these electrons travel in a fixed path called as orbits. So there are a lot of possible number of orbitals which can be found, and they are different in terms of their shape, size, and orientation. And to explain the electron, okay, you have four quantum numbers which are used. They are the principal quantum number, the azimuthal quantum number, magnetic quantum number, and spin quantum number. So let's start. So principal quantum number, it is denoted by the letter M. So the principal quantum number determines the shell, the main shell, or the level in which the electron is present. So the size of the orbital increases with increase in principal quantum number. So the size of the L shell will be bigger than K. And so obviously M will be bigger than L and K, and N will be bigger than M, L, and K. So there is it requires some amount of energy for us to shift the electron from the positively charged nucleus. So the energy of the orbital will increase with increase in the value of n. Okay, so the principal quantum number gives us the distance of the electron from the nucleus. It gives us the information on the size of the orbital and the energy which is associated with it. So it gives us the value of n, and n can be 1, 2, 3, 4, and so on. The next one is azimuthal quantum number. So the azimuthal quantum number, as we know, first of all, electrons are rotating or going around the nucleus, and so obviously they will have a particular angular momentum associated with them. So the azimuthal quantum number, which is also called as the orbital angular moment, gives us the information on the angular momentum of the electron. Okay. So where you have each shell has one or more subshells in it, and the number of subshells is equal to the value of n, that is the principal quantum number. So here, if you can see the value of L, if it is 0, then its designation is S. So its value can start from 0 and can go on. So value of 1, L as 1 gives us P, 2 is D, 3 is F, 4 is G. Now, when you have the principal quantum number value as n, okay, so it is denoted by n minus 1. Okay, so for n equals to 1, L will be equal to 0. So when L is 0, it is denoted as S. And the principal quantum number is 1, so 1s. And the number of subshells is only 1 in this shell. For the n equals to 2, it can have two values, that is 0 and 1. So it has two values, right? So here, as we saw, 0 is S, 1 is P, and the principal quantum number is 2. So it has two subshells, that is 2S and 2P. The next is 3. When n equals to 3, it can have 3 subshells. It starts from 0, so 0, 1, 2, and 3S, 3P, and 3D. The fourth one is 4. Obviously, n equals to 4. It can have 4 values. So 4S, 4P, 4D, and 4F orbitals. Okay, so the azimuthal quantum number gives us the information or determines the angular moment of the electron. Now, it also gives us the information on the subshell which is present in the principal shell. So when the number of subshells is equal to the principal shell, and also it gives us the relative energies of various shells. So basically, the S subshell will have the least energy. P is more than that. Then you have D, and then you have F. We will be talking in detail about the energy of various orbitals in the coming videos. But the azimuthal quantum number, from that we can figure out that the energy of 4F will be the highest, and that of 4S is going to be the least. So 4S is less than 4P, which is less than 4D, which is less than 4F. That is the increasing order of their energies. The next quantum number we are going to be discussing about, is the magnetic orbital quantum number. Now, basically, when the scientists figure out that electrons they behave, so they have an electrical charge which is associated with it, there is always going to be a magnetic field which is also going to be associated with it. So the magnetic orbital quantum number gives the information regarding the spatial orientation of the orbital with respect to the standard set of coordinate axes. Okay, so for any subshell, suppose we take L, 2L plus 1 values of ML are possible. So for suppose ML, let's, instead of doing that, let's come here. Okay, so let's take the value of N is 2, the value of L is 0 or 1. We know that it can have two values of L, that is 0 and 1. So the value of ML is 0 for the 0 value of L, but for 1 you have -1, 0 and +1. So this is giving us the number of orbitals which can be present, which are present in our in the shell. So the value of the ML will give us the information that S subshell has 1 orbital, P subshell has 3 orbitals, D has 5, and F has 7, G has 9. So the information about the number of orbitals is given by the magnetic quantum number. Okay, so 2L plus 1 values of ML are possible. So for ML, L equals to 0, 2L plus 1. So 2 zeros are 0. So plus 1. So you have 1 value of ML. So you have 1 subshell for, the 1 orbital for the value 0. So it is giving us, so the magnetic orbital quantum number is giving us the spatial orientation of the orbital with respect to the standard set of coordinate axes. And it also gives us the information, especially this is important, on the number of orbitals of each subshell. The last one is spin quantum number. The 3 quantum numbers which are already present gave us the information on the energy, the shape, and the orientation, but it did not explain the line spectra of multi-electron system. So 2 scientists, George Uhlenbeck and Samuel Goudsmit, proposed the presence of a 4th quantum number, and it's called as the spin quantum number. So apart from the mass, intrinsic spin, charge and mass, intrinsic spin angular quantum number. So this quantum number is a vector quantity and it can have 2 values, that is +12 or -12. So this value is basically and it is in our electronic configuration, we represent it as upwards arrow and downwards arrow to show its spin. So basically you need to remember that in these quantum numbers, the spin quantum number is very unique. So each orbital will have either a +12 or a -12 orientation of the electron. Okay, so in this video, we learned that N defines the shell, that is, the principal quantum number defines the shell, determines the size of the orbital, and also the energy. Next one, there are n subshells in the nth shell. So L, that is the azimuthal quantum number, identifies the subshell and determines the shape of the orbital. I will talk about the shape of the orbital in the coming, I think in the next video. ML designates that is the magnetic quantum number, designates the orientation of the orbital. For a value of L, the value ml has 2l plus 1 values. So this basically gives us the number of orbitals in each subshell. ms, on the other hand, gives the information on orientation of the spin of the electron. So it might seem very difficult to grasp at this concept, but these quantum numbers are the basis for us to understand the electronic configuration of various atoms. So if you haven't understood, try and revisit the topic again. Also, one very important thing is that uh, the orbitals which are present. Yeah. So with that, we finished this in this video where we learned about the various quantum numbers. In the next video, we will be learning about the shapes of the orbitals.